Hey, welcome to The Explainer. Today we're breaking down a pretty fundamental concept in chemistry, vapor pressure. And you know what? We're going to do it using an intuition you probably use every single day.
So let's kick things off with something you've definitely experienced. You walk into a coffee shop and that incredible smell just hits you. But have you ever stopped to think why a steaming hot cup of coffee smells so much more potent than an iced coffee? Well, the answer has everything to do with this invisible force called vapor pressure.
All right, so what is this stuff anyway? Honestly, the easiest way to think about it is as the smell of a liquid. That smell is literally caused by molecules at the surface of the liquid making a great escape, jumping into the air and turning into a gas, or vapor. And all that escaping vapor creates a little bit of pressure right above the liquid. And here's the key takeaway, right? The more molecules that escape, the higher the vapor pressure. And the higher the pressure, the more those smelly vapor molecules can make the journey from your cup to your nose. So a stronger smell means higher vapor pressure. It's something you can literally sense.
Okay, to really get a feel for this, let's cook up a little thought experiment. We'll call it our tale of two beakers. All right, picture this. Two beakers, both sealed up. In beaker A, we've got nothing but 100% pure water. But in beaker B, we've got a solution. It's mostly water, sure, but we've also mixed in a little bit of methanol.
Okay, pop quiz. Above which of these two liquids are we going to find more water vapor? Just take a second to think about it. Where are there more water molecules hanging out at the surface ready to escape? I mean, it's got to be the pure water, right?
Yep, you got it. In beaker A, the entire surface is water, so those molecules have a wide open door to escape. But in beaker B, some of that surface is now occupied by methanol molecules. It's kind of like they're getting in the way, blocking some of the exits. So it just makes sense that the pure water will have a higher water vapor pressure.
But here's where it gets really cool. We can do more than just say it's lower. We can actually predict exactly how much lower it's going to be. So let's run the numbers.
Let's put some actual numbers to our solution in beaker B. Let's just say it's made of 9 parts water and 1 part methanol. That means that out of every 10 molecules in that beaker, 9 of them are water. So if you look at it visually, our solution is 90% water. And that number, that 90%, that percentage is the key to this whole thing.
Okay, to do any math, we need a baseline. So let's just say, for the sake of argument, that the vapor pressure of pure water, like in beaker A, is 20 units. We'll use a unit called torr, but don't worry about the name. Just think of the number as 20.
All right, this is where you get to play chemist. If the pure stuff has a pressure of 20, but our solution is only 90% water, what do you think the new pressure is going to be? I mean, it just feels like it should be 90% of the original, right?
And boom, you nailed it. 90% of 20 is 18. Our gut feeling tells us the new vapor pressure should be 18 torr. You just figured out some serious chemistry just by using common sense.
You know, this whole intuitive thing we just did, where we just kind of reasoned it out, well, it actually has a super formal name in chemistry. We basically just stumbled upon a famous scientific law.
It's called Raoult's law, and really all it's saying is exactly what we just figured out. The new vapor pressure is just the original pressure of the pure stuff multiplied by its percentage in the mix. That's it. So this is what it looks like when you write it out all fancy. I know it might look a little scary with the symbols and everything, but trust me, it's exactly what we just did in our heads. Let's just translate this real quick. P's solution is just the new pressure we're solving for. That X is the mole fraction. That's just our 90% written as a decimal, 0.9. And that last part with the little circle, P naught, that's just a symbol for the pressure of the pure liquid, our 20 torr. See? You already know what all this stuff is.
So we've got our guess, we've got the official law. Now let's plug in our numbers and prove that our intuition was spot on.
It's a super simple 3-step dance. Step 1, find that mole fraction. 9 divided by 10 is 0.9. Step 2, grab the pressure of the pure stuff, that's our 20 torr. And step 3, just multiply them together.
So we take that 0.9, we multiply it by the 20 torr from the pure water, and what do we get?
There it is, 18 torr. This is so cool because it shows how the official formal math lines up perfectly with what we just figured out using our intuition a minute ago.
You know, the person who originally explained this, from Chad's Prep, said it perfectly. The whole point was to get you to see it conceptually first, because once you understand the why, the how, the equation is a piece of cake. Okay, but hold on a second. We figured out the vapor pressure coming from the water, which is 18 torr. But remember, there's another liquid in there, the methanol. It can evaporate too. So what about its vapor pressure?
And the answer is, well, we actually can't figure that out yet, not with the info we have. To get the methanol's pressure, we'd have to use Ralt's law again, but this time we'd need to know the starting vapor pressure of pure methanol. And this brings up a really key point. Every single liquid in a mix contributes its own little bit of vapor pressure. They each follow their own Ralt's law, which leads to the next big question, right? How do you add up all these different pressures to get the total pressure above the liquid? But hey, that's a story for another explainer.